in 9.2, we're looking to estimate a population mean this time. So um, in 9.1, we were estimating a population proportion, where the best way to estimate the population proportion was using the sample proportion p hat. Here, it's very similar. The population mean, so we're going to assume that's mu. We denote it as mu, but we're going to assume it's unknown. So suppose we were interested in the average male height in a population or average test scores in a population. Again, same as prior before, it's very time consuming to try to collect population data, and it's also very expensive to do. A lot of resources required in order for us to gather that population data. So instead, we estimate it by using sample mean, okay, x bar. Now, in order for us to do that, we're going to approach it very similarly like before, where we're going to take sample statistics, and because sample statistics can change depending on the sample that you take, okay, we want to create that region once again. So with some confidence based on our sample being x bar, we believe with some confidence the population mean is somewhere within that interval there, okay? But in order for us to do that, we actually need a new distribution, okay? So we've discussed binomial distribution, we've discussed normal distribution. In order for us to be able to calculate or estimate a population mean using the confidence interval, we need what we call a t-distribution, okay? Or student's t-distribution, either way. But the t-distribution is used whenever sigma is unknown or whenever we have a small sample size. Typically, that sample size is less than 30, okay? Now, luckily, it does follow some properties of the normal distribution, okay? If you notice, it looks very similar. Here, the very bottom curve is a t-distribution whenever sample size is 5. Right above it, this is t-distribution whenever sample size is 15. So if you notice, the more and more that we increase the sample size, the closer and closer it gets to a normal distribution, okay? But it does follow similar behavior, okay? So the shape will change based on the sample size. We're going to start using what we call degrees of freedom. I'll show you what that means in a bit. We are symmetric and we are centered at 0. The area under the curve is 1. It's, again, very similar to what we've seen before. And then once we get to the 30, as sample size increases, we begin to approach the normal distribution. Okay, and that's called the central limit theorem. Now, going down to constructing the confidence interval. This looks very similar to what we did before in 9.1. Okay, there's going to be x bar that we need to calculate, sample standard deviation, sample size. Some of these things will be relatively manageable in order to obtain. But this thing right here, very familiar, like z alpha over 2, this is a t alpha over 2. It's a critical value for the t distribution. Okay, so before we actually go into calculating the confidence interval, we're going to practice finding these t values. Okay, we're going to practice finding these t values. So let's practice. And I'm going to show you 2 ways to find these t values, one using calculator and one using the table approach. So here it says find the t value for the following. Here we have n equals 16 with a confidence level of 90%. And we're also told that we have an area to the right. Okay, so why is this important? Remember that the shape of the t-distribution depends on the sample size. Okay, now what we're going to start using is something called degrees of freedom. So degrees of freedom will affect the shape of the distribution, where degrees of freedom is equal to sample size minus 1. And this notation right here can also be df the calculator will be basing the shape of the distribution based off the degrees of freedom. Okay, so if n is equal to 16, degrees of freedom is 16 minus 1, which is 15. Okay. Also, the confidence level being 90%, they're telling us that we have an area to the right. What that means is we have an alpha. Okay. This is a t distribution. This is, and we should call this capital T. Okay. So the t value that we want to find is actually right here whenever alpha is the remaining of the 100%, if that sounds a little bit familiar. Okay, if confidence level is 90%, alpha should be the remaining 10%. And notice, it follows the same behavior as before where you're centered at 0. So we should expect, if this is a number line on the axis, centered at 0, we should expect this t value to be positive. Okay, so I want to show you two ways to find this t value. The first way is a calculator way. There is a new calculator function that I want you to look for, and the calculator function is called inverse t. If you remember the function of the inverse norm, its purpose was to find these missing bounds on the z-axis, right? Same thing here. The purpose of the inverse t is to find these missing t bounds. Okay, so I'm going to show you where to find it. So let's go to the calculator. Second, vars, number 4. Now, the reason I'm showing both ways in order to find these missing t bounds is because the TI-83 does not have the inverse t function. Okay, so I'm going to show you how to use the inverse t for those of you who have the 84, and if you have the 83, I'm going to show you how to use the table approach to find the missing t bounds. Now luckily, whether you have 83 or 84 in the next video, everyone will have a nice calculator function to find the confidence interval. Okay, just like before, hand approach is nice, but the calculator, whether you have the 83 or 84, will calculate your lower and upper region for the confidence interval for mean. Okay, so that is the good news. The inverse t is just for the specific t bound, but everyone will have the entire confidence interval function in the calculator. Now, for those of you who have the inverse t, let me show you what we need. Two things. We need an area and we need df. Keep in mind df is n minus 1, degrees of freedom is n minus 1. So the area to the right is 0.10. Degrees of freedom, 16 minus 1, which was 15. And we're going to paste this, and then we'll hit enter. Okay. What that's going to do is it's going to find the missing t bound. Okay. But notice how the calculator gave us the bound. It gave it to us in a negative number. But by going back to the curve, okay, once again, we should expect that our t bound should be positive. So by symmetry, this missing t bound is equal to positive 1.34. Okay, so by using the inverse t function, this requires two things. We need area with degrees of freedom. So once we plugged in 10% in decimal form, 15 degrees of freedom, we got positive 1.34. Okay. Let's practice another. Let's look at part B. Okay. Part B now says we have sample size 28, confidence level 85%, and we also have an area to the right. Okay. So what that means is we have a t distribution with some degrees of freedom. let's make a note of the degrees of freedom. By the way, if sample size is 28, degrees of freedom should be 27. Okay, it's always n minus 1. And we're told that we have an area to the right. Once again, we have a right tail distribution where if confidence level is 85%, what should the area be? Alpha is equal to the remaining 15%. We're centered at 0 on the t-distribution, and we have a t-bound that's missing. Okay, so for the t-bound, to find this, we need to use calculator, but now I want to show how to use a table approach as well. Okay, so the table approach, you'll have to go to MyMathLab and you'll have to get the tables and formula sheet, okay, the one that you see here, and I need you to look for table 7. We're going to look for table 7. Okay, so if you notice, when you go to table 7, we're going to zoom out a little bit. You'll see this right here, t-distribution, okay? And by default, the table has area to the right. So what that means is if you're centered at 0, all the bounds are going to be positive in this table, okay? So the way the table is read, okay, we take the first column and the first row, that's going to be degrees of freedom with your area. We'll cross-check where they meet, that's going to be your missing bound. So for example, in this problem, we have degrees of freedom of 27. So we actually need to go to 27, which is right here. Okay, that's going to be the degrees of freedom. So now the row of interest is going to be where we see that 27 down here. Okay. Next, we're going to take the area of interest. Notice that we have an area of 0.15. So we look for the area on the top row. 0.15 is here. And we will go down and cross-check where the two meet. Okay. They meet at this value right here, 1.057. So by using the table approach, t with some degrees of freedom and area was equal to 1.057. Very nice, because the table approach also gets us that missing bound. And if you wanted to, we can also verify the previous example. Remember when we got the 1.34? Let's go back to the previous example just to check. And in this example, we had an area of 0.10. So we would be on this column here, and we're looking for degrees of freedom of 15. So if I go down and if I cross-check with 15 degrees of freedom, okay, right here, we would be at 1.341. And if you notice, the calculator also got us 1.341. Okay, it's a very nice approach. Either way, we just need to know what side of the t-distribution are we on with respect to the center. If you're on the right, expect your bounds to be positive because you're centered at 0 on the number line. If you're on the left, you should expect your numbers to be negative if you're centered at 0. Okay, so either way, very nice. Let's look at one more example. I'll have you practice part C. I do want to practice part D because it does change a little bit. So we have sample size is 22. Let's go ahead and make a note what the degrees of freedom should be. N minus 1 is 22 minus 1. Okay, 22 minus 1, let's call it 21. They give us a confidence level of 80%. Let's go ahead and make a note of the alpha. Alpha should be the remaining 20%, right? Let's put that in decimal form. And this time we're told that we have an area to the left. This time we have an area to the left. What does that change? Okay. Your area to the left, now you have a left-tail distribution, where the left-tail distribution has an area of 20%. And if your missing t-bound is here, okay, what should we expect if this is my number line centered at 0? We should expect that missing t-bound to be a negative number, right? So both approaches will work, okay, either way, but your missing t-bound can either be an inverse t, where this time we use area of 0.20 with degrees of freedom of 21. Okay, just to practice using the calculator. So if you have the 84 second bars, number 4, this time our area is 0.20. Degrees of freedom is 21. Okay. Here, it's giving us a negative 0.859. Okay, let's call it negative 0.86. And again, we need to determine, though, calculator is limited on the sign. It doesn't tell us how to interpret it, but based on the position of the bound, we should expect our bound to be a negative number. So this is negative 0.86. And very similar, if we use the table approach, okay, we need to look for area of 0.20, which is here, and we will cross-check this with degrees of freedom 21. So when we go down here, okay, they also get 0.859. Let's go ahead and call this to 3 decimal places as well. Okay, so let's do this. 59. That works. And notice that the handout, the formula sheet also got us the 859. But once again, drawing the t-distribution curve lets us know whether that t should be a positive or negative. So this drawing here will be important, area to the left, area to the right, in determining what the sign of the t value will be.